Hello student, in this video lecture we are going to analyze the indeterminate frames by flexibility matrix method. So this is a question, take EI constant. So this is a single bay frame, portal frame with the two loads, one vertical load 20 kN at E, then one horizontal force 10 kN at B. The first and foremost thing is we are going to determine the degree of indeterminacy or a degree of redundancy of the structure and also choose the redundant. So, it is a portal frame. So, end A is fixer and D is pin support. Okay. So, at the fixer end there may be three reactions. So, fixer end offers both the translation and rotational restraints. So, therefore, two reactions will be created. Okay, one vertical reaction, one horizontal reaction, then one moment reaction. Then at the end D, it is a pin support, it offers resistance against translation. So, therefore, only two reactions are created, one is Vd, another one is Hd. Okay. So, degree of static indeterminacy is equal to external indeterminacy plus internal indeterminacy. This is a general formula, external indeterminacy plus internal indeterminacy. So, external indeterminacy depends upon support reactions and available equilibrium equations. Then internal indeterminacy depends upon number of closed cuts, so which is 3C. Okay. So, in this problem there are 5 unknown reactions are there, Ma, Va, Ha, then Vd, Hd, then available equilibrium equations, 3 equilibrium equations. It is a 2-dimensional system. So, only 3 equilibrium equations are available, summation of H equals 0, summation of V equals 0, then summation of M equal to 0. Then number of closed cuts, in this single bay portal frame there is no closed cuts. Okay. So, 0 number of closed cuts. So, therefore, the static indeterminacy is equal to 5 minus 3 is equal to 2, or we can use the formula static indeterminacy, degree of static indeterminacy ds is equal to 3m plus r minus 3j. Okay. So, each and every members have 3 unknowns. Okay. So, one is axial force, then shear force, then bending moments. So, therefore, 3m, then each reaction have only one unknown. So, therefore, 1 times r, then each joints have 3 equilibrium equations. Okay. So, therefore, 3j. So, these two are number of unknowns, this number of available equilibrium equations. Okay. So, in this portal frame, so there are 3 members. So, AB, BC and CD, 3 members. How many joints? Joints are 4 joints, A, B, C and D. There are 4 joints. Then equilibrium reactions, unknown reactions of 5. Then substitute M, R and J. So, degree of indeterminacy is equal to 2. Okay. Then let us choose the support reactions Ma and Hd as 2 redundant. Out of 5 unknown reactions, we have to choose 2 as redundant. So, other 3 are determined from equilibrium equation. Okay. So, in this problem we have chosen 2 redundant reaction, that is Ma and Hd as 2 redundant. Then step 2, remove the redundant and assign one coordinates in the direction of each redundant. Okay. So, at the fixed end we have to remove the redundant, that is Ma. So, after removal of that redundant Ma, it becomes a pin support with coordinate assigned as 1. It is a rotational coordinate, moment coordinate. Then at the pin end we removed Hd. So, after removal of Hd, it becomes a roller support. Before it is a pin support. So, removal of horizontal reaction becomes a roller support. Now, assign the coordinate 2 for that horizontal reaction. Then develop the flexibility matrix. Okay. This flexibility matrix is determined by in this problem we determined by unit load approach. So, Fij is equal to Fji is equal to integration of Mi Mj dx divided by Ei, where Mi is the bending moment at any point due to unit force at the coordinate I, Mj is equal to bending moment at any point due to unit force at coordinate j, then Ei flux rigidity, then integration, it includes all the portion of the structures. Okay. So, for this, so in order to develop this flexibility matrix, we have to make a table like this. So, first column of the table is portion, second column is origin, third one is limit, fourth one is flexible rigidity, fifth one is M1 and M2. So, in this case only two assigned coordinates. So, therefore, we write up to M1 and M2, we write up to M2. Okay. So, M1 is the moment induced at every section due to unit force applied at the assigned coordinate 1. M2 is the moment induced at the every section due to unit force applied at coordinate 2. Okay. So, first we are going to determine M1 value. Okay. For in order to determine My, we have to apply unit force. Okay. It includes both the forces and moment. Unit force at the coordinate 1. So, our assigned coordinate is the moment coordinate. So, that is why we applied unit moment at the coordinate direction 1. Okay. So, only at the coordinate direction 1. So, it is a primary structure. Now, after removal of redundants, okay, so it becomes a primary structures and we applied unit moment at the assigned coordinate 1. So, first thing we have to determine the support reactions. Okay. So, apply equilibrium equation, summation of moment equals 0. So, from that equilibrium equation V d is equal to minus 1 by 6, we determine V d is equal to minus 1 by 6, then summation of V equals 0. So, V is equal to plus 1 by 6, then summation of H equals 0, H is equal to 0, H is equal to 0. Then after determining the support reaction, we determine the bending moment and each and every portion AB, BE, EC, then DE portion. Okay. So, first we written DC portion. Okay. So, DC or CD portion. So, let us consider section XX. So, let us consider section XX. So, which is x distance from D. Okay. So, let us write the bending moment equation on the right of the section XX. On the right side there is no horizontal force. So, only one vertical force. This vertical force, it can't produce any axial, it can't produce any moment. So, moment is equal to force into perpendicular distance. So, this axial force have no perpendicular distance. So, therefore, bending moment is equal to 0. Then EI is already known 0, EI is constant. So, first we consider DC portion, origin is D. So, limit is 0 to 4. At D x is equal to 0, at C x is equal to 4, then flexural rigidity is equal to EI, then M1 is equal to 0. Then for CE portion, so again let us take a section XX, so which is x distance from C, or D. Okay. So, now bending moment at the section XX is equal to, so sorry, then what is the limit? So, its limit varies between 0 to 3. At C x is equal to 0, at E x is equal to 3. Then bending moment is equal to, on the right of this section XX, we have only one force, one vertical force, V d is equal to minus 1 by 6. So, moment is equal to minus 1 by 6 into x, minus 1 by 6 into x. So, origin is C, limit 0 to 3, EI is constant, then M1 is equal to minus x by 6. Then for BE portion, okay, next portion is EB portion. So, again take a section XX, so which is x distance from C, okay, x distance from C. So, what is the limit? So, at E x is equal to 3 meter, then at B x is equal to 6 meter. Then bending moment at section XX, on the right of the section XX is equal to minus VD into x, okay, that is minus 1 by 6 into x. So, again, so origin is C, limit is 3 to 6, EA is constant minus 1 by 6 x. Then finally, for AB portion, so let us consider section XX, which is x distance from A. Okay. So, origin of this portion of column is A, limit it varies between 0 to 4, at A x is equal to 0, at B x is equal to 4. Then bending moment on the left of the section XX is equal to this 1 kilonewton meter moment creates hogging moment, then that is minus 1, then HA is 0. So, therefore, it can't produce any moment, then V also can't produce any moment. So, therefore, the final M1 is equal to minus 1. Then now determine the M2 value. So, for this we should apply unit force at the second coordinate direction only. For M1 we should apply moment, that is unit force in the assigned coordinate direction 1 only. So, for M2 remove that applied moment in the previous case. Now, we apply a unit force in the assigned coordinate direction 2 only. So, now determine the bending moment for each and every portion. So, again for DC portion. So, let us consider section XX, so which is x distance. So, sorry. So, after applying this unit force, again we should determine the support reactions. Okay. So, this support reaction is determined from equilibrium equation. So, after applying equilibrium equation, VA and VD is equal to 0, HA is equal to 1. Okay. So, now write the bending moment equation for each and every portion. So, let us consider section XX, which is x distance from D. So, origin of this DC portion is D. So, limit varies between 0 to 4, at D 0, at C it is 4. Then bending moment on the right of the section is equal to 0, 1 into x. 1 into x, it creates a hogging moment. So, therefore, minus x. Then for CE portion, consider section XS, which is x distance from C. So, origin is C, limit is varies between 0 to 3, then bending moment is equal to this 1 kilonewton force acts at a distance of 4 meter from our section. So, it creates sagging moment minus 1 into 4, minus 4. Then for EB portion, again consider section XX, so which is x distance from C, limit varies between 3 to 6, then bending moment is equal to again minus 4, minus 1 into 4 meter, it creates sagging moment minus 4. Then for AB portion, so again consider section XX, which is x distance from A. So, now limit varies between 0 to 4, then bending moment is equal to minus 1 into x. Then finally, determine the element of the flexibility matrix. F11 is equal to integration m1 dx divided by A, where I and j are 1. So, therefore, it becomes m1 dx divided by A. Then substitute m1 values for each and every portion, then finally integrate it, it gives f11 is equal to 6 by A. Then f22 is equal to integration of m2 dx divided by A. Then substitute m2 values for each and every portion A, B, DC, then CE, then EB, then AB. And after integrating it, f22 is equal to 138.67 E. Then f1 to f21 is equal to integration of m1 m2 dx divided by A. Then substitute m1 and m2 value. So, finally, f1 to f21 is equal to 20 divided by A. The final the flexibility matrix, it is a 2 by 2 matrix. Okay. So, there are two assigned coordinates. So, therefore, the order of the matrix is 2, it is a 2 by 2 matrix. Okay. So, it is 6 by EA, 20 by EA, 20 by EA, 138.67 by EA. Now, remove the redundants and find the displacement in the direction of assigned coordinates due to the given loading. Okay. So, now remove the redundants and determine the displacements and the assigned coordinates. The first assigned coordinate is a moment coordinate. So, we should determine the rotation at the assigned coordinate 1. Then second assigned coordinate is the force, horizontal force. So, we should determine the displacement translation along that force direction. Okay. So, after removal of redundant, it becomes a primary structures. Then apply external loading. Okay. So, first and foremost thing is we should determine the support reaction. So, for this we have to apply equilibrium equations. So, apply 3 equilibrium equations, summation of m is equal to 0, summation of v equals 0 and summation of h equals 0. Then by unit load method, theta is equal to integration of m capital M small m1 dx divided by E I, then delta is equal to capital M small m2 dx divided by E I. So, if you want to determine slope means we should apply moment at the required direction. Then if you want to determine displacement, that is translation, means we should apply unit force along that direction. So, capital M is bending moment due to external loads, then M1 is equal to bending moment due to unit moment applied in the direction of required slope, M2 is equal to bending moment due to unit force applied in the direction of required slope. Then again you make a table, or you may use the previous table. So, we should include only one portion, that is capital M portion. Okay. So, after determining support reaction, now write the bending moment equation for each and every portion. For DC, again write DC portion. So, for DC portion, let us consider section XX, which is x distance from C, so x distance from D. On the right of the section XX, bending moment is equal to 0. Then for EC portion, so again consider section XX, which is x distance from C, then bending moment on the right of the section is equal to, so only Vd into x. Okay. So, Vd is equal to 16.67, so 16.67 into x. Then for EB portion, again consider section XX, which is x distance from C. So, bending moment on the right of the section is equal to Vd into x minus 20 into x minus 3. Then finally for AB portion, so for this again consider section XX, which is x distance from A. So, bending moment on the left of the section XX is equal to HA into x, where H is equal to 10 into x. So, bending moment equations. Then finally slope in the assigned coordinate direction 1 is equal to integration of capital M small m dx divided by E I. Okay. So, apply this for entire portion of the frame. So, substitute capital M and small m1 value for each and every portion. Finally, slope is equal to minus 205.04 by E I. Then deflection and the second coordinate is equal to integration of capital M m2 dx divided by E I. Substitute for each and every portion. Then finally, after integrating it, delta 2L is equal to minus 1053.57 divided by E I. Then the final equation, the redundant reaction is equal to flexibility matrix inverse into delta 1 minus delta 1 L, then delta minus delta L. Okay. So, substitute delta 1 and delta 2 is equal to 0. This is the net displacement at the assigned coordinate 1 and 2. Then substitute the values R1 and R2. R1 is the first redundant, that is MA, then R2 is the second redundant, HD. Then substitute the flexibility matrix, then take inverse of it, then also substitute delta 1L and delta 2L. Then after multiplying this flexibility and displacement, the redundant MA and HD is equal to, MA is equal to 17.039, HD is equal to 5.14. Then after determining these two redundant, now determine the other unknown reactions. So, with the help of equilibrium equations. So, apply 3 equilibrium equations, summation of h equals 0, summation of v equals 0 and summation of m equals 0. So, finally, HA is equal to 4.86, then VA is equal to 6.17, VD is equal to 13.83. Then after determining the support reaction, you should draw the bending moment and shear force diagram. Thank you.